right, cool. Ages ago, a long, long time ago, in a classroom just right here, we were working on this 4-bar linkage. We came up with like this equation that for given angles and angular rotation rates. How did we get there? What's going on here? How did we find constraints? Like, is this just something that you have to memorize for these kind of systems? You just have to know this equation forever if you ever want to work on it again. How did we get here? What was that? Yeah. The ratio? How is what are the ratios? Like what do you mean?
Everything was proportionate to L1 and our point O is fixed, so it's point C, so it's a fixed distance that they can go away.
Okay.
Point O.
Okay.
C. And that was proportionate to L1.
L1 over what? What's the proportional? Does something
L1 over the distance from O to B.
From O to B over. Is that constant? Not constant? So then how do we get to like equations that are constraining motion? How do we get to constraints? Sometimes like ratios of things work out. Like if you have like a gear ratio, R1 is 10 centimeters, R2 is 20 centimeters, then maybe there is that ratio of like R2 over R1 is going to be the same difference in speed from like rotation of one to rotation of the other. So here when we have like gear ratios, R2 over R1 that's always 2, and it's also equal to R2 times, or wait, it's also, sorry, like theta dot 2. Let me double check. I'm just trying to make sure that I do this correctly. So R2 theta 2 dot equals R1 theta 1 dot. So we can use like for a gear ratio like that, we can set up a constraint equation that like one gear is always going to move twice as fast as the other gear. So depending on if you're using internal combustion engine, then your drive side is the 10 centimeter. Output is like gearing down. So you spin your engine spins at 1,000 RPM or 2,000 RPM. Your wheels are spinning at now just 500 RPM. Or
Smaller gear moves quicker.
Yeah, smaller gear is going to move a lot quicker because for one full rotation of that big gear, the chain has to move the same distance. Like the connecting part, like this velocity and that velocity. The chain, in order for the chain to remain tight, those two velocities have to be equal to each other. And in order for that to be true, R2 times theta dot has to be R1 times theta dot 1. So that would be a place where you could use like ratios directly of like one gear to another gear, and that would work. But here we had something a little different because we had
RO equals RP plus C over K.
Yeah, we started looking at like what are the vector like how do these vectors all connect to each other? Yeah, and really like any combination of vectors it'll get you to the same equation. Like you'll still end up with some kind of like L1 theta 1 dot cosine and a sine and all that. RA, RB slash A, RB from C, and then this is that RC. Kind of just backing up before we start like plugging in numbers again. The more, so like the numbers that we get of like how fast is link 2 rotating and how fast is link 3 rotating, that's the goal, but the process of getting there is a lot more important, of understanding how, when you create like a pin connection like this, what is that doing to like the motion of this system? How is it constraining that motion? Yeah.
Wouldn't the speed of link 2 be L2 minus link 1 divided by link R times the velocity of link 1?
So say that again. Let's try.
L2 minus L1.
L2 minus L1 is?
That would be the distance that way past L1.
Okay, and what's it? That's
Divide that by L1.
Divide by L1?
Yeah. And then can you multiply that by the velocity of L1 to get the velocity of L2? Or is it L2 minus L1 not necessary?
That would sometime, like if we compare this equation to this one, if let's say cosine theta was 1 and cosine theta 2 was 1, then we would have this case of like an L2 and L1 here. But yeah, it's still, yeah, it would be a little different. And then if L3 happened to be L2, like equal to L2 or something. Yeah, so it's better to stick, like, write out like what are the vectors involved in the motion, and then start working from there. And even when I was thinking about like this gear ratio of like, I knew that gear ratios, that's the end result, that the ratio of the radii should be ratio of the speeds, and also related to ratio of the torque. But I start off with this idea that the chain is all moving at a constant speed, and that's my constraint. That the chain, because if the chain had different speeds, like if V2 was more than V1 here, then it's breaking, like something is stretching the chain and snapping it, or something, or maybe it is just stretching, like a rubber chain. So that would be different. Now I have like a spring acting as a chain. So it can't change length. The chain has to be like just, at least in an ideal. In reality, yes, if you apply a force, everything stretches. That's just a fact of life. But a lot of times the amount that it stretches is negligible compared to all the other stuff happening. So when you apply a torque, the chain is definitely going to stretch, but it's usually stretching by a millimeter, and you're talking about like how much power is being generated over 1,000 RPM. So you're losing a little bit of slack and tension to stretching and release, but not compare. And I mean, once you have like a little bit of chain tension, a lot of that goes away anyway. If you're super into like gear ratios and chains and cogs and sprockets and optimizing chain alignment. Doesn't look like I have any takers on this. Nobody's flipping their fixed gear upside down to like line up their chain to increase efficiency from 98 to 99%. No, you do have to. I mean, if it's a single speed, you have to play around with like a little bit. You can put spacers on either side, and you can change like where the chain ring is up front. And anyway, this is the fun stuff. Okay, so then we started plugging in a whole bunch of numbers. We had 2 equations with 3 unknowns. And then there were like all those sine and cosine stuff. But if you know where things are, then you know sine and cosine. Maybe not directly, but the information's there. We just have to like dig through and get it. So we spent some time doing that. Then we had a third constraint that theta 1 dot is always doing the same thing. It's always rotating at 10 radians per second. So now, what are these 2 like numbers? We need theta 2 dot and theta 3 dot. Do you know what those? Can anyone? What are they? What is? Yeah, it's revolution. So it'll be measured in like radians, but you can also, if you have 2 pi radian, that's 1 full rotation. So when I say like theta 2 dot, what is that describing in here? The rate. Okay. Yeah. How much it's moving around. Theta 3, how much it's moving around. Are those numbers going to be constant? Like theta 2 dot? You think? We have constant theta 1 dot. So theta 1 is going to move around and it's always 10, no matter what. But if the angle theta 2 changes, does theta 2 dot stay the same? So let's pull up. So as you take a look at this, think about like that angle theta 2 opening. So when theta 1 is increasing at 10 radians per second, moving in a circle, is this link number 2 moving in a circle? So there's got to be something, like it opens and it closes. So that means that it depends on what the angle is, right? Like the solution is. And so we're solving for like one snapshot in time of like what is the speed at this point, but to keep in mind it's not constant. It's going to change as soon as those angles change a little bit. Now we have a new speed. All right, so what do we think? What are these numbers? Theta 2 dot, theta 3 dot. How did we get there? Yeah. Yeah, we just had like 2 missing values, right?
We have in terms of we have 2 values.
Yeah.
We can plug in the list. We can know how to
Makes sense. Yeah. Makes sense.
So why did you do this week or when we next week?
That one is just representing changes in momentum. So like MA and it could be like I times or whatever the moment of inertia is, like moment of inertia times change. It looks the same because it's the same units. I guess MA is like the only difference is you're writing out what are the terms of MA. Yeah, that's what you meant. That one also, yeah, that one.
There is, you do have the ability to pay that.
Oh, it has like negative. So yeah, what's the negative? Yeah, so number 1, 2.
L, I think you're on L1. Do you have all those values? L1 and 2, I think.
Opening faster than
What's L2? 1 minute. What's L3? 1 minute.
Yeah. Oh, should. So I don't know how you solve like sets of equations, but one way is set it up as like linear algebra problem. Take everything you know, throw it on one side, call that B. Everything you don't know is like in some matrix, like called A. So I can say NP lin alg dot solve A comma B. And then I get like 1 radian per second and 2.5 radians per second. That's what I end up with for my results. And I'm pretty sure everything looks right. That would be like theta 2 dot. At least from, this is what I get when I plug in the numbers that I have, unless there's a typo. Have you seen this before? Like setting up like sets of equations like this? Yeah. No. So if I have like 10 plus 3x plus 2y equals 0, and 15 plus 2x minus 4y equals 0, that's 2 equations, 2 unknowns, and I can start splitting this up into a linear algebra problem. So I take my magic arrow and apply some magic. And I'll keep these over on, take those two constants, put them over here on my left-hand side. Now I'll have a 3 and a 2, and a 2 and a -4. Times that like x and y, so that I can ask the question of like, what is x and y if this is A and this is B? And if I tell like something, either MATLAB, Python, even your graphing calculators will do the same thing. If you give it a matrix and a vector, it'll solve it for you. Solve a set of equations. Fun to like learn a new way of solving equations, right? The nice part is like even if I had 20 equations and 20 unknowns, it's still the same process. Set up that 20 by 20 matrix and then say solve this for me.
Question.
Yeah.
Is that 2 under the 3, the 2 from the 2x or the 2 from the 2y?
So this is
That 2 under the 2.
so like when I multiply matrix times vector, I take this row times this column, so that turns into 3x plus 2y, and then this row times that column turns into 2x minus 4y. Yeah. It's a nice, if you haven't tried it, then like give it a shot. If you're like, this is all some witchcraft to me, I like to solve for one, plug in with the solution into the previous equation. It works, you'll get there. Even if you have 3 equations, 3 unknowns, you end up doing the same math, but this can save some time. Oh wait. Okay, so how fast is this? Is 1 radian per second rotating quickly, slowly, mediumly? Pretty fast? Our input is 10 radians per second. So the little crank thing is moving a little over, it's like 1.5 rotations per second. So not super fast, like not I don't know, centrifuge sort of fast, but it's moving. And then this is 10% of that. This like little connect, and this is the connector arm, that first value. Then the second value is our bigger arm. If we wanted it to move faster, what would we do? Like, what do you think? Bring it closer to each other. Shorten that L2, bring them closer. This is part of the project. We'll play around with like geometries and then the motion stuff. But yeah, make that one a little closer so that maybe it bobs more. I don't know. We'll find out. Introduce weight. Yeah. Yeah, smaller links, less weight. Unless they're all massless links. Yeah. Alright, cool. So then rinse, lather, repeat, right? We just have one more. And this one looks exactly the same, but it just took that point C and moved it down by like half a meter. But it's the same 3 links, just mounted in different locations. Or quarter of a meter, sorry. Yeah. Oh yeah, and RC should be 1 and negative, yeah, negative 1/2, right? It should be negative 1/2 to match the video. So dy is negative 0.5. Oh yeah, let's do this. RO is 0, 0. RA is 0 and 0.25. RB is almost 1 and 1/2, or 0.97. 0.97, 1/2. Yeah, right, 97. And then RC is 1 and negative 1/2. So we have something looks roughly like this. It's not really to scale because there are link 1 and link 2 are supposed to be the same length, but here they're all kind of stretched out. What do you think? Where do you start? It's the same question. How fast is, oh yeah, let's write out our givens, right? Theta 1 dot is 10 radians per second. I want to know how fast is link 2 rotating and how fast is link 3 rotating. So where do you start? What are you going to do first? Yeah.
How can you get it the 1 meter when you go a meter down and then 0.03 meters across?
And then, sorry, what was it?
For B to C, your linkage from B to C, you go a meter down and then 0.03 meters across, and you have to link.
You're going from B to C.
You go from 0.5 to negative 0.5 for your Y.
Yeah. Yep.
And then you go from 0.97 to 1, which is 0.03 meters.
Yeah.
And so if you do that math, you're not going to get a meter at all.
Yeah, it's about a meter though.
Okay.
Yeah. Give me my cursor, man. Or wait, sorry, we want 1 squared and 0.03 squared, right? So it ends up being 1.0004. So depending on how many sig figs we have, still 1 meter. Yeah. But yeah, when you square something that's like less than 1/10, it becomes now less than 1,000. So we're still, yeah, we're not breaking too many laws of geometry. Just stretching them just a little, just because of the sig figs. Where do you want to start here?
Start writing down there.
Do the vector addition again?
Yeah, that would work.
Yeah, yeah. Start back in there. Okay, yeah. Do that, like check to see how vectors out. Okay. Yeah. Yeah. That makes sense. Yeah. All right, nice. So there was a lot of people kind of went back to like what we first started with, like, all right, let me start drawing out these vectors. I can do the same kind of analysis here, right? And then say RA, and this is RB/A, this is RB/C, this is RC. And when I add those up, it's the exact same equation that I had before. Oh, if I could actually write RA plus RB/C minus R, oh my god, B/A minus RB/C equals RC. That was exactly what we had for the other 4-bar linkage kind of thing, which means that that same equation it's still going to hold. So I can jump right into, I mean, you can do it. I think it always helps to kind of draw out what you're planning to do. So I think it helps to at least like write this as you're getting started, and the more practice the better. But I can jump right into the fact that, all right, I already know how to solve, like I already went through the work of figuring out how to define this set of equations and how to set up these sets of unknowns. So I can jump right into that equation. And then the question comes back to like, all right, I know where these things are like in my Cartesian coordinate space. So then I must know something about the angles. And then I have to figure out what are those sine and cosine components again. But we did a lot of the hard initial like build up work already. And that's always nice when you can like rinse off and reapply the same way. You get to the same spot. Oh, like how did we get there? Oh, okay. Yeah, so that one. So moving around in a circle. X equals R cosine theta, Y is R sine theta. Dot is same R. R theta dot times sine theta. Yeah. And we can do that for all three links because they all follow the same that same like relative positions as we take a derivative for them. They all end up with that same definition. Yeah, and they all have, instead of R, it's like L. And it's like some length away from where they're connected to. No. Okay, yeah. Yeah, A3 makes them sort of bigger in this configuration. I would think small. Yeah, I was thinking that. They're the same numbers, but opposite signs. Yeah. Yeah. Usually it has to do with like just a sign error carrying constant from one side to the right side. Didn't multiply one, then carry it over. But I think your intuition is right, because theta 3 should definitely be opening, and then theta 2 is closing really slowly. Yeah, like really small. Yeah, that makes sense. Yeah, they're both, I guess. Okay. Yeah. Yeah, and zero is fine. Zero is good. And one is nice. Yeah. Yeah. No. It's always getting stuck. All right, cool. So nice part about having two like basically vertical things is that our sine component, sine and cosine, is either 0 or 1. So like cosine theta 3, that's 1. Sine theta 3, that's 0. Theta 1, like cosine theta 1, that's 1. sine theta 1, that's 0. What does that tell me about theta 2 dot? Got to be pretty close to 0, right? Like maybe, like as we were kind of looking at before, it's not exactly 90 degrees, but it's pretty darn close to 90 degrees. So this theta 2 dot should be pretty close to 0. And that makes, it does make this system of equations a little easier to solve, because now it's just, now we get that ratio, I think that you were talking about earlier, like how you can take the ratio of things, because I could say L1 theta 1 dot is L3 theta 3 dot, at least within a couple of sig figs, like 2 or 3 sig figs. So kind of cool. Works out nicely. And a little less like cumbersome math of like Charlie up at the whiteboard connecting all the dots. 112, 110. 2 minutes over? Sorry, you'll get it back. Well, I'll give you 2 minutes back at some point, I swear. Thanks for like, homework, we set it for I think tonight, to turn it in tonight. But now I think we're all done. Like I think everything's wrapped up. If you still have questions, you can always ask, and you can always put a note in a submission of like, hey, I still need help. Can I work on it? And that's totally fine.
I had a quick question.
Sure.